All right, welcome back to System Software. We're going over how on CodeGen 3 we can use this wrapper that I've given you in order to test this part of the compiler, just the arithmetic and branching without having the full compiler written. So it basically gives you a template, a precompiled template of this IR file. So this IR just declares a function, a set of local variables. It calls print int, this C function that I've implemented here for you. It just prints an integer. I think we talked about this last time. And then it returns 0. So that's what this IR function does, and I've given you a precompiled assembly version of this. It's broken into two files, wrapper end and wrapper start and wrapper end. Why would it be in two pieces, this IR? Why wouldn't I just give you the assembly? Why bother breaking it into two files? Yeah. Not quite. So if I compile, let's say I compile this program where I say result equals 10. What's this assembly file going to contain, the compiled version of the assembly file? What's the first thing that it contains? Yeah. Yeah, all the assembly metadata and the function prologue, and then it's going to contain the compiled version of this assignment. And then what's the end going to contain? Yeah. What is it? No, the files I've given you is the compiled assembly version of this. So as your colleague's saying, when you compile this program, you get the function prologue, and then you get this assignment here, and then you get the call statement, and then you get the epilogue in return. So what I want to do here is I want to allow you to put your code here, but be able to plug that into a precompiled function. And so the function has a prologue and an epilogue, so we at least need something before and after your compiled version. Let me get a full version here to show you what I mean. This is CodeGen 3. So if you look at this IR, the beginning of the function is the prologue and all the parameter handling. That's the beginning. And the end is the epilogue and return value. So the part of the compiler you're working on today is the part that does arithmetic and branching statements, which are always inside of the function. So if you just don't compile the function part, then you're not going to have a complete assembly object file. So I've given you the beginning and end of the assembly file, and then you'll put your compiled content in between the beginning and end of the compiled assembly function. Does that make sense? Does that kind of make sense? So this is the full IR program. You're only compiling this part. So I've given you the compiled versions of this and this. The stuff that comes before and after the content you're compiling. Does that make sense?
So that's the function name is main.s?
Yeah, I mean, if you remember when we compile a function, this gets compiled into this assembly code. Defines the function and gives you the prologue. So if you want to compile this whole thing, you'd have to compile all of the constructs in the language. This project, you're only compiling these constructs. So I've given you pre-compiled versions of the constructs before and after the content. Anyway, so there's a little explanation here describing if you want to read it in more detail, but I've given you these wrappers. The start is just the beginning of a function. It has the function prologue and definition. And the end has this part, the call to print int and all the return stuff in epilogue. So it's all this stuff at the bottom of the function. So you can use the wrapper by just following these instructions. Just download it, unzip, untar it, and then if you follow these directions, this is the template that I gave you, main.ir, and then you can just add your code here where it says add your code here, and do not change the ones where it says do not change. And then you can just use the make file to build the wrapper. So if you just follow those directions, it will give you this wrapper.elf binary, and you can just run it and test your program. Test what you've compiled. And it'll print out whatever you put in the result variable. So this is what you might see if you tried to keep your CodeGen 1 and CodeGen 2. There'll be two definitions of main. So if you just follow these directions, you should be able to use the wrapper. Just put your code here after this comment. Put whatever value you want to get printed out into the result variable, and then build and compile with your compiler. Yeah?
Is the wrapper just used so you can compile your program faster?
No, so you can compile your program without having to implement CodeGen 1 and CodeGen 2. So there's 10 or 15 compiler functions. In this project, you only have to implement 3 of them. But in order to have a complete program that can be compiled and run, you need to implement functions. So in lieu of doing that, I've given you a precompiled function. And these instructions will put your compiled versions of just operations and branching inside of this precompiled main executable. So if you want to do this sort of by hand, you can follow these instructions. You can run your compiler and save it to some file. I call it main.s.body. And then you can use the cat command. What does cat do? Does anyone remember what cat does? Yeah, it just prints files. It prints the files in order that you give on our command line. So it prints the start of the precompiled wrapper, your body that you compiled, and the end of the precompiled wrapper. And then it redirects them into main.s. And then you can compile as usual. Link with iolib.c because that contains the printint function. So if you want to do this by hand, you can follow these directions. And I think this is what I've done. Yeah, this is what I've done in the self-check. So if you run the self-check, you'll build up this .s file by hand. So don't worry too much if you don't completely understand the wrapper, but it's just because you're only compiling part of the language, I've given you the precompiled versions of the rest of the language for a specific program. Yeah.
So first we do the test of the arguments, and at the end we add the code for the wrapper.
I don't know what you mean by the argument. What arguments?
The parameters, the compiling parameters.
No, there's no parameters. It's just a main function that defines locals.
Yeah, that part.
Yeah, this is given to you, and the enter locals function is given to you in the template, in the code template up here. So don't worry too much about the details of it. You can read over this and try it by hand. I suggest just trying it by hand, and then you'll kind of get it. I think it'll make it easier to get. But if you just follow these directions, you should be able to test without having CodeGen 1 and CodeGen 2. All right, questions on this? So that was a good question. Any questions on branching? We went over last time, how branching works. What assembly instruction corresponds to if go to, or what assembly instructions? Okay, jump, so jump, what does jump do?
It takes you to a specific label.
Sometimes or always?
Oh.
Always. So what can we use that for conditional go-tos? No, you can't, because conditional go-tos only happen under certain comparison. So recall that this is what an if go-to looks like. You have a condition, and then only if this condition holds do you do the branch. But in the Intel world, a jump, JMP, is an unconditional branch, so it'll always branch. So yeah, what instructions do we use for if go to?
You have like the compare function, and then you have all the different types of jumps.
Right. You have compare followed by one of the variations of jump, one of the conditional jumps. So this is like a template of what it looks like. You populate operands. I have RAX and RBX, call the compare function with bad indentation here, sorry. And then you call the corresponding jump corresponding to the condition. Yeah?
When you use compare, do you have to use RBX and RAX?
No, it'll take any legal operands.
What does it like do mathematically?
It just subtracts the arguments.
Oh, okay.
So it works just like a subtraction, except it doesn't save the result of the subtraction.
So how does it know like when to use
What's that?
It sets the flags when you use compare.
Yeah, so every operation sets some flags in a kind of hidden register in the machine, which is, you just have to read the manual to know this. But when you run a subtraction or an addition, this special flags register sets things like, was the result 0? Was the result negative or greater? And even though you won't directly look or copy data or process data from that, these jump operands will look at that flag and determine whether to do the jump or not based on those flags. And so we use a subtraction, if you remember from last time. The reason we use subtraction is because we're effectively converting a comparison like this into this, because there's a flag register that tells you whether it's 0 or not, or whether it's greater than 0. And so we do a subtraction and then effectively compare to 0. And those flag registers will give you various comparisons to 0 of the result of the computation. It's just how the architecture is designed. All right, other questions on branching? Okay, so that was Code Gen 3. And you have all the instructions here. Hopefully you have the way to test it. I'll be grading it with assuming that Code Gen 1 and Code Gen 2 aren't there as well. Maybe I'll do some work to pull out your functions. I don't know yet if I have time to write the grading scripts to do that. But I'm thinking that maybe another bonus project could be having a complete compiler, since in the course of the class we don't never really get to put together the complete compiler officially, but that could be like a bonus project, a complete compiler. Of course, it depends on getting all 4 of the projects right, but that could be one potential project. Yeah, you just put them all in one CodeGen file, and then you'll see the full compiler for the full language working. All right, other questions on CodeGen 3, branching, arithmetic, CodeGen 1, CodeGen 2? So I think CodeGen 1 is graded, and then CodeGen 2, yeah, CodeGen 2 is due this Thursday. Remember to get something committed before that time, even if you're not done. And I'll try to get grades out on Friday for that. Okay, and I've also put up CodeGen 4, so it's the setup is very similar to CodeGen 3, except we're going to be doing the pointer parts, the pointer compilation of pointer operations to assembly. And so these are kind of, on paper, pretty short functions, but pointers I know are always confusing, a confusing part of C. And so the tricky part here will be just getting the concept right in order to do the compilation correctly, and then testing it. Yeah.
Functions long?
No, the functions are very short. Just like with CodeGen 3, the functions are generally short too, except if go to, you have to test which condition you're using. But the functions are really quite short. But understanding them is the key. And so that's what we're going to go over today. Is we're going to go over how pointers work, and we're going to see this at the assembly level. And I think hopefully, if you've been confused by pointers in C, seeing it at the assembly level will actually, I think, make it easier to understand what's going on, because you're not working at this kind of high-level abstract version of pointers. You get to see at the physical level, at the machine level, what's happening with pointers. And they're actually pretty straightforward. It's just trying to reason about them can be kind of confusing. But once you see how this works, with the stack frame and with assembly operations, I hope and expect that it will be a little easier. So who struggles with pointers, or who doesn't like pointers, or wants to admit it? Who loves pointers and totally gets it? Okay. Okay. Well, So for you, you'll see how this actually works at the machine level, and actually a little bit why the language is designed the way it is, and also why the assembly language is designed the way it is, because it's designed around handling pointers. So what are pointers, to get this started? What are pointers in like C? Yeah.
They're access to the addresses in that whole piece of data.
Yeah, they're addresses. They're addresses. I mean, that's really all they are. They're really addresses. In the C level, you can think of them as addresses to variables. But now that we've done some compilation of variables, what are variables in the low level? What are variables? Yeah.
Also addresses?
Yeah, they're also addresses. So this is where things get a little confusing, because we have several sort of layers of addresses going on. But hopefully today we'll go through it slowly and carefully, and hopefully you'll have a good understanding, or at least a good basis, so you can go through yourself how pointers work. Yeah.
We're doing this both days this week?
Yeah. Yeah, so I today I'm going to cover like reference and dereference, and next time my plan was to cover pointer assignment. But we'll just go, as we go. I think I wanted to leave lots of space and time, because pointers are so confusing, to make sure we get a good understanding of how they work. And then you have to compile them. It's another kind of meta level of reasoning you have to do, because you're not only reasoning about the pointers in the program you're compiling, but you have to do this for all programs. So it gets kind of abstract and a little mind warping very quickly. But okay, so let's take it concretely. Let me get the slides up. Yeah.
If pointers are used so frequently in so many different programming languages, why do they never call them pointers?
Yeah, like references and stuff.
Oh, yeah, that's a good question. I don't know. I mean, pointers are the C world name for them.
C is the only class where they'll ever just call them pointers.
Well, Java, I guess the thing is, Java, you don't explicitly work with pointers. Everything is a reference, or everything is a pointer. But I think pointers are when you explicitly manage them. I think that's probably why.
So is the difference a reference is the actual address, whereas the pointer is the variable contained?
Yeah, I think so. I think that's probably a good way to say it. That makes sense to me. Here we go. Okay, so let's first look at the semantics of pointer operations in simple IR. They work basically just like C. So we'll do a little review of C as well if you don't remember this. All right, so what does ampersand do in C? Let's do some, yeah.
It returns the address of the variable in memory.
Returns the address of the variable in memory. Now, when you're working with C, you don't really have a notion of what this variable is. It's just some symbol on the page, and you just are told that in the mental model of the machine, these variables correspond to addresses somehow. Now, we know how they correspond to addresses. So for a local variable like x, where is it stored, or how is it stored in memory? Yeah.
It's stored in the stack frame.
Yeah, that's exactly right. It's stored in the stack frame. So this reference, at least for local variables, is actually just getting the address of this variable that it's associated with in the stack frame. Okay, so now what kind of data type does T1 hold after this assignment? An address, yeah. Now at the machine level, everything is just binary data. You can think of them as binary numbers, I guess, but it's really just bits, sequences of bits. So in terms of if you look at the data, you won't be able to really know for sure whether it's an address or a number. And it turns out it's really just how the data is used. And we'll see at which assembly instructions we use in order to treat something as an address. But semantically, this T1 is now holding an address. And so what is an address? Just to make sure we're all on the same page, what is an address?
Location of the variable in memory?
Yeah, it's in memory. So remember, memory is just each memory slot is a byte addressed memory. Each byte is given a number, some sequential number from 0 up to however much memory you have, and that number is the address. That number corresponding to the byte in memory is the address. Yeah.
This is tangentially related, but when you say you have a certain amount of RAM,
Yeah.
is the RAM basically just for the stack? It's all the memory addresses that you have to build the stack with?
It's not just the stack, it's also the heap, so malloc.
Okay.
It also stores the program code itself, the machine code of the program, and any statically allocated.
So it does a lot of different things.
Yeah, but it's it does. It's used for a lot of different things. But you can think of the stack and the heap as just different ways to manage data with a programming language at runtime. All right, questions on the reference operator. So it gives you the address of a variable and then stores it into whatever the left-hand side is. Okay, so dereference, I call it dereference. There's multiple ways to do dereference, but I call it dereference in simple IR. So what does a dereference do? If I have some variable T1, what does dereference do?
So it goes to the location of the address and gets the value of the address.
Right, so if T1 has some value, and this is where things get very confusing, because T1 itself, the variable, is an address. It corresponds to some address in memory. But in that location is a number, and when you use the dereference operator, you're telling the machine to take that number that's in the memory slot associated with T1, treat it as an address, follow that address, and get the data from that address that's given at T1. Yeah?
So it's kind of similar to like when you have the stack line on RBP.
Yes, exactly right. And in fact, RBP effectively is a pointer. And when you get an offset, you're dereferencing it. You can also think of the RBP as an array, because what is an array? An array is just a pointer. And when you do the index, it's just adding the offset to that pointer and then dereferencing. All right, questions on dereference. So we don't have multiple pointers in this language, but you could emulate them with several temporary variables. So C has also multiple layers of pointers, which makes things even more confusing. But you can always break it down into individual pointers.
Are you saying like double pointers?
Double pointers, triple pointers,
So
yeah.
you can't have like a 3D array?
You can, but you can't express a triple pointer in this language. You would have to dereference. You'd have to do the individual dereference operations yourself, one at a time, for each layer. Yeah.
For each dereference operation?
Yep. And that's what's going to happen at the assembly level. So the assembly level, there is no assembly instruction for triple dereference for me. There's only a single dereference.
So any compiler that does like work on C would automatically realize it's a triple pointer?
Yep. And it'll unwrap each dereference one at a time, one instruction at a time. In the same way that if you have a long mathematical expression with 8 different arithmetic operations, the compiler, the assembly does not have an instruction for 8 operations at the same time. Well, outside of single instruction, multi-data or vector operations, but in kind of the classic ALU, it's one arithmetic operation at a time. And so you'd have to use temporary variables to help you do that. Okay, questions on dereference, the meaning of dereference. Okay, so, and then we have what I call dereference assignment. So I just needed to make a distinction between when we're loading a value using a dereference and when we're storing it. So what's the difference here? What does it mean to store or have a dereference assignment? Yeah.
And this one, basically, you're doing is you're basically pointing to the original address and storing 11, the value 11, into that address.
Yeah. So in the same way in the previous one where T1, which is a variable, something stored in memory, its contents are an address. And then when we assign to the dereference of that address, we don't assign to the memory associated with T1 itself. We look up the value of T1, that value is an address, and then we go to that memory location, and that's where we store whatever's on the right-hand side. So this is a constant, so we'll just store 11 into whatever address T1 holds. So I'll show this, I'll diagram this all out, but this is where things get confusing because variables themselves are, in a sense, like a reference. I mean, they are a reference. They map to some memory location. And so what gets confusing is that you have a map to a memory location holding a memory location. That's where things get confusing. And then, of course, if we have a variable on the right-hand side here, we're going to have to load that value from memory and then store it into the dereferenced address from T1. All right, questions on just the semantics, kind of high-level semantics of this. I'll go through, we'll diagram all this together, but the questions on this. Yeah.
What about double pointers?
Yeah, so as I mentioned before, the machine will only handle a single pointer at a time for you. So if you had a double pointer, you would just do each dereference one at a time. So you'd first dereference the first pointer, store it into a temporary, and then dereference that temporary variable. And you can do that however many times you'd like. So just like with arithmetic operations, you can think of multiple dereferences as being broken down into individual operations at the machine level. Okay, so let's do a little test. Here's a complete example using all three. I have a single function here. I set x to 8, y to 9. All right, so when I run t equals ampersand x, what's the value of t1? Yeah, the address of x. And now I assign the dereference of t1 to t2. So what's the value of t2? 8. Good, because t1 holds the address of x, and when I dereference that address, I get the value of whatever was in that address. Good. Okay, so star t1 and x are like kind of equivalences. They're aliases.
Like the star cancels out the ampersand.
In a sense, yeah. It's like you get the reference and then you dereference the reference. Yeah. You can think of you could think of it that way. All right. So now, what does this do? I dereference assign t1. Yeah.
Now x equals 11.
So x equals 11. Why does x equal 11? Because t1 holds the address of x, and I do a dereference assignment to that address. So even though I don't have any explicit operation on x here, because t1 is aliased to x, or that is it has the same address as x, I've now assigned x to 11.
You could just think of like addresses like boxes around the variable.
It's one way to think of it. You can think of it as boxes or arrows pointing to them. Yeah, there's several visualizations. I'll do the kind of arrow-based one because I'll show you the stack frame. And then if you sort of reason on this at like the individual step level, it'll make it easier. You don't have to kind of try to think conceptually, okay, what's the value of x? You can just step through one operation at a time and hopefully get the right answer that way. All right, questions on this complete example showing all three? What's that? Yeah, good question. What does it return? So this assigned x to 11. This assigned t3 to 11. It's not touching the value of x. And then, yes, this returns 11. Yeah, I forgot to answer the question. Yeah, it returns 11. Oops. Okay, so let's review stack allocation. So how are function local variables stored at runtime? On the stack. Okay, so let's draw the stack for this example. All right, so I'm going to try to do this in as much detail as possible. So let's. All right. So what goes on this? What's the first thing in the stack frame? Yeah.
Return address.
What's that?
Return address.
Even before return address.
Base point?
Base point is a register.
Old base
What does the caller add to the stack?
parameters?
Parameters. Yeah. There's actually parameters first, and then the return address. And what's the next thing on the stack frame?
Local bars?
There's something else first. Yeah. The old base pointer. Yeah. Pointer to the old. So I'll just call that old RBP. And if I've set this up correctly, the current RBP will point to the stack frame entry that holds the old RBP. Yeah.
Shouldn't the parameters be in the register because you only have 2 of them?
First six.
Okay, that's a good question. So good point. Good point. So for this example, there are only 2 parameters. So you're right. The first thing. Okay. Good point. Good point. So I was conflating asking in general versus asking specifically. So you're right. The first thing in this stack frame would be the return address. You are right about that for this example. I thought I was asking a trick question, but I wasn't. So this is yeah, you're right. This example doesn't have them, so forget about parameters for this one. Okay, and then what's next on the stack?
Local vars?
Yeah, the local vars. So conceptually, there's a slot for each of these local vars, and I probably made way too many here. So let's give these physical seeming addresses here. Let's just start at let me move this aside for a second. Let's give these physical seeming addresses. So they wouldn't be this low in memory space on a real machine. But here, if I can add 8 properly, okay, so let's say this, and of course I did this wrong because it actually counts down. It counts down from high memory addresses. So let's do it. Let's do it this way. All right, did I do my math right? What's that? Relatable? Yeah, that's why I like computers. I don't have to do math or calculation. All right, so what's the value of RBP? 80, address 80. So these are like decimal addresses. So RBP holds the literal binary representation of the integer 80 to represent, I mean, there's nothing enforcing what it represents, but we as a compiler writer are using it to represent the memory location that's addressed at 80, decimal 80. Questions on this so far? There's a little slightly more concrete view of the stack frames. Okay, so this is our stack frame layout refresher. And these symbols here, these are not stored anywhere, except for debugging symbols. These aren't stored anywhere, don't have to be stored anywhere in the assembly file. These are just the mappings that the compiler has. Actually, what mappings does the compiler have at runtime for A and B and C, et cetera? So what does the compiler store for these? Yeah. It stores offsets from the base pointer. So let's call this the symbol, and I'll put the offset here for each of these. So this is offset -8, -16, -24. Let's see, is this what I had? I want to make sure this lines up with what I put in the actual examples. -24, okay. -24, -32, -40, -48, and -54. All right, questions about this? Yeah.
Does that say T1, T2, T3, or F1, F2, F3?
This says T1. I just have very bad handwriting. So this is the actual address in memory for a specific run of our program. Yeah.
I don't mean to be negative here,
Yeah.
but should be negative if we fix. Sorry.
Yes. Did I mess something up? Yes, you're right. Thank you. Okay, questions on this? So this information here, this is what the compiler is holding, and it's going to use this to generate instructions that do stores and loads as offsets for RBP whenever we have just regular variable assignments and variable usages. These are not pointers per se. These are just what the variable usages without pointers get mapped to. All right, questions on the setup here? Excuse me. Okay, so let's take a look at, I have a refresher here for assignment. So how does assignment work in assembly? If I've got, say, let's say I just have an assignment like x equals 7. And let me get rid of the highlighting. If x equals 7, what happens to the memory? Yeah.
You gotta move 7 into like a temp register and then move that value into the offset pointer, correct?
Okay, so that's how I did it. So you can move it into a temporary register, and then we move whatever that value is into. Do you remember how we did the assembly to store into a variable, store specifically into the variable x?
So -24.
Okay. Yeah, -24 RBP. Yeah, exactly right. So this is what we used, this move instruction. This is how we stored whatever the value of RAX is into whatever the runtime address of x is going to be. We don't have to know what this address is. We just have to just use RBP and an offset from it, 24. Yeah.
I just want to make sure you also like at the start have to like subspace for all this stuff. Right?
Absolutely. Yeah. Yeah. So the prologue, I'm assuming that this is assuming that the prologue has run an allocated space for it. So because the runtime value of RBP is 80, this 80 minus 24, if my math is right, will work out to be address 56. So this is why we don't need to know these addresses at compile time. We only need to know the offset and maintain RBP every time we have a function call, maintain it correctly. All right, questions on this? All right, so that's how normal variable assignment works. Now let's make things more confusing by looking at how we do assignment from, or should we look at assignment from a variable first? Would that be helpful? Sure. Okay, let's look at assignment from a variable. So let's say we have, let's do T3 equals X. So how would we load from X? Yeah.
You do the same thing except instead of the 7, you do the offset and then like that the offset for X.
Exactly. So we'd use this. Yeah, exactly. We use this same register, indirect, offset, whatever the official name for it is. You'd use this same operand, which gives you the offset of -24 from RBP, save it into some temporary variable, and then do the same thing we did before to store this into whatever T3 is. So T3 here is -56 from the base pointer. And voila, we've got an assignment of x's value. Remember x's value, okay, so I made it 7 here. And then I moved whatever this value was. I addressed it using this register indirect offset from RBP and stored it into RAX and then stored that value into this offset, -56 from the base pointer, making this 7. Questions on kind of normal variable assignment? All right, so now let's make this. Yeah.
With the temp register, can you choose, or is that just the function?
You can choose. You can choose. I tried to make it simple by having everything be RAX and RBX, even though RBX is like technically callee saved, which makes it a little more annoying. But yeah, you can use for these move operations. They'll take any register. Okay, so let's take a look at now how we get a reference to a variable. All right, so in this example, what is the address of x? 56. Do we know that address at compile time?
No.
What do we know at compile time? Yeah, I think you were first.
You know it's offset from the base pointer.
We know it's offset from the base pointer. Oh, what else do we know? Yeah.
The address of the base pointer?
Well, we don't actually know the address of the base pointer. But what do we know about the base pointer? Well, it'll change during runtime, yeah.
Its offset is 0?
No, the base pointer it's just a register. Yeah.
Points to the old base pointer?
Well, yeah, I mean, actually, that is actually correct. It's always pointing to the stack frame. It's always pointing to the address of whatever the stack frame is. And we design RBP to point to the stack frame entry, the middle of the stack frame entry that holds the old base pointer. So the point is that RBP always points to some address where these fixed offsets will give us the variables for our function local variables. So we know that RBP holds the address that points to the stack frame. And we know the offsets. We know the actual concrete numbers of the offsets. So the trick is that if we want to get the address of X, we can use the fact that we know RBP is going to hold a pointer to the stack frame and the fact that we know the offset of X in order to generate code that computes the address of X at runtime. With me so far? So we're going to generate code that we know, because we've guaranteed RBP points to the stack frame, we're going to generate code that we know will compute the address of X. Even though we can't know, in general, the address of X at compile time, we can use what we do know, that RBP will always point to the stack frame, and we know the fixed offset of X. We'll use that to generate code that will compute the pointer for us, the pointer address on our behalf at runtime. Make sense? So this is the tricky part about compilers, is that you won't be able to, in general, write a compiler that computes the answer for you. So what you'll do is you'll use some clever logic to generate code that will compute it for you at runtime. So there's no plus symbol in assembly, but we can generate code that we know will compute the arithmetic that our developer asked us to compute in our language. Okay, so let's see the steps for this to work. We'll start with RBP because we've generated code using a convention that will ensure that RBP always holds a pointer to the stack frame. So RBP holds an address. We'll generate code that adds the offset of our variable to RBP, and then we'll just save that result, because as soon as we've added the offset to whatever RBP is, voila, we've got the pointer, we've got the address of our variable. Okay, let's see how this works in our diagram. So we'll just use informal assembly here. So what are the steps? We take RBP and let's get rid of this. So we take whatever RBP is, so the kind of like pointer to X is whatever RBP is plus whatever X's offset is. I can say like symtab, well, I'll just say offset of X.
So really, it's subtraction.
Yeah, it will end up being subtraction, yeah. So what's the offset of X in our table here?
24.
-24, and what's RBP in our current execution of the program? 80. So it'll be 80 plus -24. What do we get? 56. And is that indeed the address of X?
Yeah.
It is. It is the address of X. So our goal is to generate code that will compute this for us, for whatever our variable is. So let's first look at what the assembly will be for this offset. So, we'll save RBP into a temporary register because we don't want to blow it away. We don't, remember arithmetic in the assembly world or in the Intel world, only 2 registers. So you're going to overwrite one of the registers. So we're going to save the value of RBP into RAX. So now RAX, equals RBP. And then how do we do addition? Well, we know how to do this, right? We just use the add instruction. So what's the add instruction look like here? Yeah.
RAX plus the actual value from -24.
So it'll be RAX plus equals 24. How do we express that in assembly? Yeah.
Move the offset, add the offset to RAX. So RAX is the second.
Good. So yeah, remember the second parameter is the left operand and the destination. So this is how we express RAX plus equals -24 in the Intel world. And so now RAX holds, or will hold at runtime, it'll hold the pointer to X. Yeah.
So in the assembly, we're going to
Yeah, yeah, because these offsets, at least in our language, we're guaranteed, we design it so that the offsets are fixed from RBP. And those fixed offsets are just numbers, and we can use an immediate to compute that. Okay, so now RAX holds our pointer, our address. So what do we need to do to finish up this reference assignment?
Save it.
Save it. Save it to where?
T1.
T1. Good. So how do we save RAX to T1? Yeah.
Move RAX into negative 40 RBP.
Good. Negative 40 RBP because our offset of T1 is negative 40. And if you just remember this as a kind of idiom, this operand here is how you store and load to variables. They're offset from RBP. Yeah?
How come you can do that in one instruction and not, you don't have to do two separate ones?
You mean the negative 40 RBP? It's just the design of Intel. So Intel is like CISC, complex instruction set versus RISC, reduced instruction set. It just gives you these sort of higher level assembly operations that'll do multiple steps for you. There are other architectures where that's not the case, where you'd have to, I think, actually I haven't done much ARM compiling, but I think you'd have, I don't know if they have register offset. I'm actually not sure. But you can imagine other architectures where you don't have this complicated instructions that can do many operations for you. And actually under the hood, I think Intel is using microcode, a kind of RISC architecture under the hood, and then it's translating or interpreting your high-level assembly instructions into that. All right, questions on this so far? So let's review. Our goal here was to assign the address of X to T1. That's what the reference operator does in C. And in our runtime here, our actual address of X is 56. But depending on when your function is called or how often it's called, this address may not be the same every time you run the program. But what will be the same is that RBP, assuming the compiler is correct and no attacks, RBP will always hold a pointer to whatever the current stack frame is for the function. And we also know that these offsets are fixed because we designed the compiler that way, to use a fixed offset for every variable. So in order to assign this address, 56, to T1, we can generate code that will compute the address for us at runtime. And that code is this. It will take RBP and add the offset of X to it. Questions? Questions about this? Yeah.
So if we wanted to send this address value to another program, would it just work, or would we need to
Another program? You mean like a different process or the same process?
A different process.
Oh yeah, You won't have, you don't have guarantees that the function has the same address across processes. I mean the data across processes. Well, I guess so for one thing is if this function were called multiple times, if it were called in different places, then even in the same program, X may not have the same address for every call to F. Imagine factorial. You have factorial, the address changes of the stack frame address changes for every call.
Yeah, but if you just have the address in memory and you wanted to let another process use that address, would it just work automatically?
Oh, so this is the virtualization of memory. Yeah, this is what you learn about in OS. So processes have their own virtual address space, basically starting from 0. And so without additional help from the kernel, you can't even read the memory. You're not supposed to be able to read the memory from other processes. This is process isolation. Now there are vulnerabilities where you can subvert that, but that's one of the protections that the kernel provides is isolation between processes. So even if you knew the address, you should not be able to read it. You'd end up reading your own address space's address. Now there are kernel features like memory mapping what is it, memory mapped? I can't remember what it's called. There's like, shared memory. There's shared memory. So you can allocate a space of memory that's shared between two processes. And I think they'll have the same, if I'm not mistaken, I think they'll have the same address. So there's a function called mmap. So I am not much of a kernel hacker, but I think you can share, you can share these, and I'm pretty sure the addresses will be the same across them. So this creates lots of headaches if you're trying to do now if you're doing multi-threading, it's easier because of the same process, but across processes, pointers will cause issues if they're not in the same addressed memory. This also causes issues with persistence, like trying to store data to disk. Like if you have some complicated data structure and it uses pointers, well, you can't just store that to disk because those pointers may not be the same addresses the next time you run the program, so you have to serialize it. There's some modern hardware called persistent memory, which is basically turning your RAM, the RAM bus is actually accessing a solid state drive. So instead of RAM being flushed as soon as you take the signal off of it, it's persistent memory. And pointers cause a lot of headaches for that work. I think it's actually current research on how to deal with this stuff. But that's a good question. So across processes, the kind of, without any other functionality, processes have isolation, and they should not be able to read memory from other processes, and they have their own memory addressing. They have their own virtual memory space. So that's a good question. Take an OS class. Hopefully they'll go deeper into that more than I know about. Oh, operating systems. Yeah. But good question. All right, any other questions on taking a pointer? Yeah.
I'm a little confused how it wouldn't just affect the value at that register. So here, you move the value of RBP into RAX, and then you subtract 24 from it.
Yeah. Yes, we have destroyed RAX. We've updated RAX. But RAX is just, think of it as a temporary register. It's just a temporary value.
RBP holds the value of the pointer.
Okay. RBP holds this pointer.
Yeah.
Holds 80.
Subtracting from that pointer.
Yeah, we're not updating RBP. That would be bad.
Couldn't you just do the last move command, but with that 24 offset?
Okay. You mean this command?
Yeah.
Okay, what's the difference? So this is where the point. This is why doing this at the machine level will hopefully make you understand pointers more, and it's also why it's so confusing. Because variables themselves, you can think of variables as references, as pointers that the compiler manages for you. So in some sense, X is being translated, or X is being, this offset is actually a kind of a relative pointer. So in the compiler, it's actually holding an address. It's a relative address to RBP, but it's holding a pointer. So any operation you do to a variable is in some sense using a pointer-like thing, because RBP is a pointer. It's an address.
Yeah.
So this step here is just, so remember, this is register indirect. This is saying store in the address given by this operand. And that address is here, 20, what's that?
You do the math directly with the value of the address rather than referencing the offset of the pointer.
Yeah, I guess. That's one way to say it. If that helps.
The offset, doing this as offset syntax is not the same as actually editing the address.
Yes, that's right. Yeah, using this syntax is Intel's way of doing, actually, it is doing the same computation as this. It is doing the same computation as this, in some sense, because, it's not the exact same, because it's 24 versus 40. But these two instructions are doing effectively the same thing as what this operand is doing. The difference is that this operand is like a shorthand for saying, do this arithmetic for me, and then store in that location for me. So in that sense, it is like a pointer dereference, because you're telling the machine, here's an address I'd like you to update. Actually, all stores are really like pointers, because you give it an address.
But if you did move -24 RBP and then negative 40 RBP, that would put the value in the offset of the first.
Exactly. So let's make this more concrete. So I think in my program, what did this have originally in my program? 8, I think. So X holds 8, and then after I do this computation, so RAX holds 80 because that's RBP, and then subtract negative 24, that's 56, and then we store that value in T1. So now T1 holds 56. So the question was, what if we had tried to be clever and be like, all right, well, I mean, you can't actually do this in the Intel world. You can't do a load and a store at the same time. But let's pretend we could. Let's pretend we could do a store and a load at the same time. What would the result, I mean, we'd have to use RAX, as a temporary register. What would the result of this be? So we read, what would go into T1 now when we do this? Yeah. 8. Yeah, good. 8 would happen. And so this is equivalent to T1 equals X, whereas this one is T1 equals the address of X. And so that's a good question, because this shows exactly the distinction between Intel's, sort of fancy dereferencing that it does for you in order to handle variables, which variables themselves are pointers. So this is why, in some sense, it is kind of like a double pointer, because X itself is like a pointer because it's an address, or it's an address. Maybe it's not a pointer. It's an address. But then we're taking the address of this, we're getting the literal address of that thing and storing it into another variable, and that store is also using a pointer-like thing, a reference-like thing in order to do the store. So good question. So at the result here, T1 is 8, the value of X. So one way to distinguish here is say the value of X means the memory value at that location versus the address of X, which is RBP plus the offset, the address of the memory location. Yeah?
T1, T2, T3 already defined as pointers?
So this is why this is so confusing. So one thing that makes pointers different from variables is that you can think of all variables as references, because they map to some location in memory. And anytime you have an address is, it's not a pointer, but it is a reference to a memory location. What makes something a pointer and what distinguishes, say, negative 40 RBP from T1 holding the address of X is what makes something into a pointer is that the value stored in the memory is intended to be used as a reference. Is that more confusing or less? I don't know if that's more or less confusing. So one of the main problems here is that just looking at memory, there's no general way to say, well, this is an address versus this is an integer, or this is an integer, this is an address. It's all just binary data. What makes this an address is that some operation is going to use it as an address. So we've used this reference operator here, and that's what makes this an address. And as soon as we put an address as data, that's when we have a pointer. When we use an address as data, that's where a pointer comes from. So that's why this X here is not literally a pointer in C, but why T1 is a pointer, because T1's value is an address, whereas X in the compiler, yes, it uses references in order to access the memory associated with it. But the data that's stored at that address is not intended to be used as an address, whereas the data stored at T1 is intended to be used as an address, as given by the operations on it. So to show that this is a pointer, we can draw an arrow here from this data to say this data is intended to mean an address in memory. Yeah?
There's no defined way to tell what we're actually storing inside.
Not at the machine level, because it's just storing binary data.
Okay, so how we define data type, is that just how we intend to use it and not actually the...
Yeah, exactly. Yeah, data type is really an annotation of your intention about using it. And in languages that are, I can't remember the definitions here, untyped, like a simple IR, you don't make any declarations explicitly about what the data type is going to be used for. So you can think of a type, kind of in the formal definition of a type, is a set of values and a set of operations on those values. So a set of operations, a set of data, a set of values themselves, I mean, in the math world, that is like a type. You have like the set of integers. But in the computing world, a type is the data, or the type, the set of values and the operations on those values. And so that's what a type checker uses in order to validate whether you use the correct operations on the data and whether you're using them correctly. But strictly speaking, at the hardware level, you just have bits. And the only reason that this 56 is an address versus an integer is because we loaded it from a pointer reference. We loaded it from RBP plus the offset. And when we go to dereference, I mean, this is why you have problems with pointers, and actually why C will do some checking of pointers for you, but you can subvert that. I don't have it ready to go, but in prior classes I would show how we can make the compiler turn an integer into a pointer and vice versa. And you can do pointer arithmetic in C, limited amounts of pointer arithmetic. This is also the source of vulnerabilities, like stack smashing attacks, where we blow away addresses with the data that we'd like. You know, we violate the whole stack frame invariant that we've tried so hard to make the compiler respect. Oh, does that kind of answer your question?
Yeah.
Make things clear. Questions on this? Yeah.
T registers to store addresses.
Say again?
T registers.
T registers?
What do you call that? T symbols.
So this is so variables, you can think of variables as memory locations. That's why this is confusing, because memory locations also have addresses. And so when a variable is not a pointer, you never need to think about the address. The compiler is managing the addresses for you. And when you don't have pointers, the value that's stored at that memory location is never intended to be used as an address. When you have a pointer is when the values at these variable locations, at these memory locations, are intended to be used as addresses. That's what makes pointers different from variables, generally. And that's also why all languages, I guess technically all languages have references if they're working on a state machine like this. But they may not have pointers, because pointers are when the data at a variable is explicitly meant to be an address. Questions on this? Questions? Oh, wow. Okay, let's do dereference. Finish this up with dereference. Okay, we already went through this. All right, so let's look at dereferencing. All right, so how do we load a value from an address given in a register? Yeah.
You gotta go to that register and get the value, go to the offset.
Okay, it's similar to offset. Yeah.
I suppose you get the value of the reiteration that holds the pointer, so you grab that memory address, and then you subtract RBP to that to get the offset.
Okay, so we're circling around something, right? So yeah, we're going to have to get this value. This is the value that we want. Did I show the? Yeah. So so let's say we want to dereference T1. So we want to get. So well, what value will T2 hold after we do this assignment? 8, because we dereference T1, which means we look at the value of T1. T1 is meant to be an address, and we don't get the value of T1, but we take whatever its value is, and we look that up in RAM and get the value of that address, which is 8. So there's a addressing in Intel that will look very familiar. This is effectively how you do a dereference in Intel. Now, you already saw the more sophisticated version of this, the offset version of this, which is like an array. This, putting parentheses around a register, is basically just doing a dereference for you. It's saying don't copy the data at RAX, but go to the address that RAX holds and get the data from that address. Questions on that? So it's very much the same that we used for our whole variable lookup, but we're going to use it for pointer dereference. Yeah.
Did you set RBX yet?
No. Well, no, I haven't said REX. I just wanted to show the operation here. So let's go over what this will look like. So it's slightly more complicated. So we're going to get the value of the variable. So in this case, we're going to get 56. Actually, get the value of the variable. Yeah, we're going to get 56. We're going to get the value of this variable. And then we're going to get the value of the memory at that address. And then we're going to that doesn't look right. Why did I make that so complicated? All right, I'll just go over exactly what you guys said. So we're going to get this address from T1. We're going to use this register indirect addressing to get the value at that address. And then we're going to store that result in the variable that we were trying to store. So what was so T2 equals star T1. This is what we're trying to compile. So what we need to do is get the value of T1, load the value of the address that T1 holds, and then store that value into T2. So let's start with storing the value into T2. So let's assume, so this is what the code is going to look like. All right, yeah, let's just go one by one. Let me just show this address here for the sake of time. So this is how we load the value of T1, just like before. So this is the same as we've seen for loading the value of T1. It has offset -40 from RBP. So this is the instruction we use to load the value of T1 into RAX. So now RAX holds what value? RAX? It holds 56. It holds the value. So this is how we load the value of T1. So now RAX holds 56. So let me put a note here. And then this is how we take RAX and treat it as an address instead of just its data. If we didn't have these parentheses, RBX would just hold 56. It would just copy RAX to RBX. The parentheses indicate that you do a lookup to memory of whatever address is in 56. So what value do we get from parentheses RAX? We get 8. So RAX is 56. Parentheses RAX is 8. So parentheses RAX is effectively the star T1 in assembly. So this gives us the value of the address, the value of the memory at address 56, and it stores it into RBX. So we use another temporary variable here to hold our value. And then this last instruction is just storing T2, just like we saw before. So if we skipped this line here and just had move -40 RBP into RAX and then moved our AX into 40, that would just be a regular assignment between two variables. Here instead, we're first taking the value of the variable and then using this register indirect load to get the value of memory, the memory location that RAX holds, and then storing that into T1. Yeah.
So the offset is pretty much adding -40 to what's in RBP. So is there an implied 0 if it's just the RAX?
Yeah, exactly. Yeah. So this is no offset. It's just whatever RAX value is, go to that memory location. So RAX holds 56 right now. So this says go to address 56 and load its value.
So if you were to do 0 parentheses RAX is the same thing?
I think so, yeah. It should be the same thing. So this here, parentheses RAX, because RAX is 56 right now, that parentheses is saying go to address 56 and load its value, which is 8, and store it into RBX. So this is the key difference between assigning T1 to T2 versus assigning star T1 to T2. This is the star part. The parentheses is the star part. And we need an extra register to hold the address and then hold the value. Doesn't matter what they are. What's that?
That's the same reason for what I was saying earlier as well, referencing like the offset.
Yes, exactly. Yeah. All right, questions on this before we go? All right, so take some time to wrap your head around it a little bit. Look at this diagram. I'll put the diagram up, put the video up, and then, we actually got through everything that I was going to cover today. So we'll go over the reference assignment next time. All right, everyone, have a good one.